Hi, everyone. Thanks for joining. Yeah, this is the last recitation of this semester. We are almost there. So in this recitation, we'll do a bunch of review problems for your final exam. And then we'll do the same thing on Thursday during your discussions, and there'll be additional review session on Monday led by TAs. So there'll be plenty of opportunities to practice for the final. As usual, please either ask your questions in the chat or feel free to unmute yourself and just start talking and ask your question. So let me first go through the announcements, and then I'll check the chat to see if there are any questions. By the way, I apologize for the noise in the background. They're using a leaf blower, and I mean, hopefully it's not too bad. I think microphones these days are pretty good at kind of focusing, but yeah, I'm sorry about it. So the main announcement I have is about the final exam. So the final exam will be next Tuesday, December 10th, from 3:30 p.m. to 5:30 p.m. Know that unlike quizzes, you have to take the final exam during that time. So we won't have any kind of sliding window, anything like that. You have to work on the exam during that time. Now, as before, and as for quizzes, we will add half an hour grace period to this time that you can use for submission. So to scan your exam, submit it, whatever you need to do. So you'll have from 5:30 p.m. to 6 p.m. to submit your exam. As before, you can use this period only to deal with submitting the exam. You should not be working on the exam during that period. And as for quizzes, we will be really strict with late submissions. So if you miss this grace period, you don't submit in time, you don't submit by 6 p.m., we will just not grade your final. You'll get 0 points. Any kind of technical issues you might have, you have to document them using like a written letter from your internet provider or whatever. So make sure to find a place where you have good internet. Make sure that you know how to submit it. Make sure that everything is working before the final. In terms of the material that will be covered, anything that we covered this semester goes. So starting from chapter 1 all the way to chapter 7 on graphs. How to study for the final? My suggestion would be, at least go over all the questions in your practice quizzes and the actual quizzes that you had. Make sure to understand them. Then go over all of the homework problems and make sure to understand all of those. And finally, come to the review sessions that we made available to you guys. So the one that you judge on now, and the next one on Thursday, and then there will be one more on Monday. We won't repeat the problems. So what else will cover on Thursday is not what I will cover today. So make sure to join those. And then office hours will also continue until the final exam. And I'll make one final announcement about that later today. So if anything is not clear, if you struggle with any of this concept, any of these problems, please come to office hours before the final exam. And then finally, don't forget about the last homework that is due this Friday. And so these are my announcements. Any questions about any of these?
Do we still attach an index card to the back of the final exam?
Great question. And thanks for asking this. I got the same question in the last recitation, and so I'll make an announcement about it as well. So yeah, the rules for the index card are the same as for quizzes. So one sheet of paper, and you have to attach it to the final exam. Great question.
Hi, I have a question. Like I saw the practice quizzes for 7, but we don't have the quiz 7, right?
Yeah, there is no quiz 7.
Yes.
You're done with quizzes. However, we posted this practice quiz so that you can practice for the final. So the final exam will include questions on graphs, which were not covered in the quizzes.
Yes.
you
Will
can
it have an
expect-
emphasis on graphs though?
No, it won't be heavily slanted towards graphs. So we still didn't create the final exam, but we're working on it. Rough guidelines, you can expect somewhere between 10 to 15 questions. It is twice the length of a regular quiz, right? And so if you think about, we had 7 chapters, so it's kind of 1 to 2 questions per chapter, maybe a little bit more on graphs, right? But it's not going to be heavily slanted towards graphs. These are all good questions. Any other questions?
There is a question in the chat window.
Okay. I can go there and take a look. Last quiz grade. Yeah, we are working on it. I just emailed TAs today. They're kind of close to done. So I would say maybe another 2 days or something. It's just there was a long Thanksgiving weekend, and we decided not to force TAs to work over Thanksgiving and to grade over Thanksgiving. So the same as you guys, hopefully, TAs also had time to enjoy Thanksgiving and the long weekend and so on. And that's why we are a little bit behind with grading, but we are working on it. So good question. So I told them basically that by Friday, they should really try hard to grade both quiz 5 and homework 6. So you should get grades for both of them by Friday. Any other questions? Okay, so let's do our review. So I'll start with propositional logic and in particular implication. Implication we find is the tricky one that students struggle with. So remember the implication. This is the symbol for it. This arrow. The way I read it is if P then Q. Then we introduced a bunch of concepts around the implication and definitions. So negation of implication is P and not Q. Converse is Q implies P. Inverse is not P implies not Q. And contrapositive, which is the one that is particularly important because we use it in proofs. In proof by contrapositive is not P implies not Q. So why do we use contrapositive in proofs? Because contrapositive is actually equivalent to the original implication, but in many cases it's easier to prove. So contrapositive is particularly important. And then here in the bottom right corner, you can see the truth table from the implication. And as you can see, there is only one row that evaluates to false. So if P is true and Q is false, then the value of the implication is false. Everything else evaluates to true. In particular, if hypothesis is false, implication will still be true. So that's something that students find confusing, but it just follows from the definition of the implication. So make sure to remember this. And then we talked about biconditional as well, which is P is equivalent to Q. So that means that P implies Q and Q implies P. Okay, so that's our implication. So let's do one quick kind of warm-up problem. So based on this definition of implication, determine which of these sentences are true and which ones are false. And I'll give you maybe like a minute to do this. So this should be really easy. Okay, so let's do this. So how do you determine this? First, you have to think about what is P and what is Q. So this here is your P, and this here is your Q. And now we have to determine when P is true and when it's false, and the same for Q. And then we determine the evaluation of the whole sentence. So the first one, P is equal to true, and Q is also equal to true. And from the truth table of the implication, it follows, true implies true is true, and so the whole thing evaluates to true. In the second case, P is false, Q is true, and again, the whole thing evaluates to true. And in the third case, P is false, Q is true, and again, the whole thing evaluates to true. So all three of them evaluate to true. An example of a sentence that will evaluate to false would be something like, if 1 plus 1 is equal to 2, then 2 plus 2 is equal to 5. So in this case, P would evaluate to true and Q to false. And that's the scenario where implication evaluates to false. Okay, any questions about this one? Okay. So make sure that you are, really comfortable with truth tables for all operations. Of course, not just implication, so and, or, and so on. And make sure to, in particular, to really understand implication well, because we do see confusion around it. In particular, with these two rows that are maybe somewhat counterintuitive, but they follow from the definition of the implication. Okay, let's now do a problem where we need to use truth tables. So truth tables are super important. They come up in many other contexts. Even if you think about programming, right? If you have a complicated if condition that involves, and or and parentheses and so on, to truly understand this if condition, you have to understand truth tables for these operations. So make sure to practice truth tables. And this is the question that was in quiz 1. So I want to use a truth table to prove the equivalence of these two sides, and you should briefly explain why the equivalence holds. So maybe I'll give you 3-4 minutes to do this, and then I'll sketch out the truth table for you. So yeah, give it a try, and then we'll do it together. Oh, there was a question about the previous one. Should have been if F then F. Let me just go back. Yes. Thank you. Good point. Let me correct this. Yeah. So 2 plus 2 is clearly not equal to 5. So this is false. So we have false implies false, which is still true. So I messed that up a little bit. So good point in the chat. Sorry about this. Okay, truth tables. Yes, please try to do this one. Actually, while you're working on this, I will start sketching it out because it will take me a while to draw it. So in the interest of time, let me slowly start working on it. Okay. So let me go over this with you guys. So what I kind of sketched out, that's the setup, right? So a couple of things I want to stress out here. So you have to list every sub-expression that you find here as a column, and make sure that you don't skip any. Like it might be you might be tempted to skip node Q and just kind of do that in your head. So don't do that. So every single sub-expression has to be present as a column. If you miss something and you do it in your head, you're going to miss points. So that's the first kind of important thing. The other important one is that for the variables P, Q, and R, you have to list all possible evaluations. And so make sure that you don't miss anything there. Kind of have an organized way of doing it. The way I usually do it is I kind of start with the rightmost one, and I start changing false true, and then I move from right to left, right? And that's how, if I do it in an organized way, I am almost certain that I won't miss anything instead of doing it just randomly, right? And finally, there is a really easy sanity check that you can also apply here. So how many rows do you need if you have 3 variables? You need to have 2 to the power of 3 rows. So you need 8 rows. So if I count them, 1, 2, 3, 4, 5, 6, 7, 8. I have 8 rows, so probably I didn't miss anything. Okay, so this is just some suggestions for how to just structure the problem. And now you have to fill in all the rows. And I'll do just the first 2 in the interest of time, so you can move on to other problems. But let me do the first 2. So not R is false, not R is true. P implies Q, false implies false is true. Then we have P implies Q implies not R. So we have true implies true is again true. Then we have not Q, that's true. Then we have P and not Q. So P is false and not Q is true. So we have false and true, which is false. And then we have not R or P and not Q. So not R is true, P and not Q is false. So we have true or false, which is again true. That completes the first row. So let's move to the second row. Not R now is false. P implies Q is again true. Then we have P implies Q implies not R. We have true implies false. So remember, that's the row in the implication that is false. Then we have not Q is still true. We have P and not Q. So P is false, not Q is true. So this is still false. And then we have not R or P and not Q. So not R is false and P and not Q is false. False or false is false. So this completes the second row. And you continue doing this for all 8 rows. Okay, and now how do we know that they're equivalent? We have to make sure that the columns for these 2 expressions are evaluated to the same thing. And in this, for the first 2 rows, they indeed do, and you should get the same thing for all 8 rows. So that's how you know they're equivalent. And you should write a short sentence, in the exam, clarifying this. Okay, any questions about this problem? Okay, so definitely make sure to practice truth tables. And you can write down truth tables of each individual operation in your index card and get them from there, or just practice it a lot so that it really sinks in and you know them by heart. Kind of like multiplication table, right? I don't really have to think anymore, what the truth table is for P and Q or something like that. Great. So let's do some proofs. So if we want to, we covered a bunch of different ways for how to do proofs, right? So if you want to prove some proposition as an implication, there are a couple of ways to do direct proofs. So there is by construction, which is just, the simplest type of doing direct proof. And then we have proof by cases and proof by induction. So we covered all of these. And then we covered two ways of doing indirect proof, either by contrapositive, by proving not P implies not Q instead, or by contradiction. So we assume both P and Q are true. And then from there, we follow the proof until we show a contradiction. So you should know all of these different ways of doing proofs. If you're looking for a counterexample for something, we want to show that implication is false. Okay, so let's do a simple proof by contrapositive. So you want to use proof by contrapositive to show that if 3n plus 2 is odd, then n is odd. So how do you go about this? First, you write down the contrapositive, and then you prove it using direct proof. And this is a really simple proof. I'll give you a couple of minutes to try it on your own, and then I'll do it for you. But it's very straightforward, and so I would consider this to be a simple problem for the final exam. I'll try to rank the problems a little bit for you so that you get a sense for how the final exam will look like. Okay, so let me give you 3 minutes for this, and then I'll do it. I'll do it for you as well. Okay, so I hope you managed to do this on your own, but let's now go over it. So first, the contrapositive. So the contrapositive of this is if n is even, then 3n plus 2 is even. Okay, great. So let's prove this. If n is even, then it means n is equal to 2 times some k, where k is an element of integers. So that just follows from the fact that n is even. And then let's plug this into 3n plus 2 to be able to show it's also even. So that it's equal to then 3 times 2 times k plus 2. Sorry, 3 times 2 plus k. and that is equal to 2 times 3k plus 1, and that is equal to, by substitution, we know that plus and multiplication closed under integers. And so from that, it follows that we can substitute that. From that, it follows that 3k plus 1 is also an integer. And so we can substitute this with a new integer L, where, L is an integer. And so we have 3n plus 2 is equal to 2 times L. And from the definition of even, it follows that 3n plus 2 is even. And that concludes our proof. So the same as for quizzes, in the final exam, we'll give you a hint for which type of proof you should use. So you won't have to figure that out on your own. Any questions about this proof by contrapositive? So I would consider this to be a simple problem for the final exam. So that's something that everyone should be able to solve in, like 5 minutes at most. Any questions? Okay. So, this is what I often do. I don't cover the same set of problems in both recitations that I do. So in the first recitation, I covered the proof of induction, and we did a pigeonhole principle proof. So, watch the first recitation video on YouTube to see solutions for those. In this recitation, I will skip this and I'll move to do like one or two proofs about sets. So let's remember a couple of kind of basic things about sets. So a set is just a collection of distinct objects. And then there is a bunch of kind of operations we can perform on sets, and we also define some predicates. So the first one is subset, and this is the symbol. So A is a subset of B if for all x element of A implies x element of B. And we use this definition in our proofs. A is equal to B if and only if A is a subset of B and B is a subset of A. And then we also define a bunch of operations like union, intersection. This is the first one, union, and so on. Okay, I won't go through other things here. Let's instead do some proofs some proofs about sets. So let's use so-called element-wise proof to prove that the following statement about sets is true. So this set that includes all elements that evaluate to 2n plus 1, where n is element of z, intersect with 5k plus 4, where k is element of z, is a subset of 10m plus 9, where m is an element of z. So let's, I'll give you maybe 2-3 minutes to kind of start working on this on your own. And then I'll do it for you. And this one is kind of tricky. There is this little trick that you have to figure out to be able to complete the proof. But maybe some of you will be able to actually figure it out. So I would consider this to be, usually this type of proof is pretty easy, but this one is a little bit trickier. So yeah, give it a try. And then we'll solve it together. So let me see, keep an eye on time. I'll give you 3 minutes to try it. Okay, so let me try to show you how to do this one. So first of all, what is a general structure of element-wise proofs for subset, right? We want to show that the left-hand side is a subset of right-hand side. So the general structure is we assume that there is an X that is an element of the left-hand side. So it's an element of 2n plus 1, where n is an element of Z, intersected with 5k plus 4, where k is an element of Z. So assuming we have such an X, which is an element of the left-hand side, we want to, through a number of steps, show that X is also an element of right-hand side. We want to show in the end that X is an element of 10m plus 9, where m is an element of Z. So that's the basic structure, and now we have to fill in the middle, right? We have to actually derive this. So, so if X is an element of this intersection, that means that X is equal to 2n plus 1, and X is also equal to 5k plus 4. And like I said, this proof is a little bit tricky. So I kind of understand that maybe not all of you managed to derive this, because there is kind of two little tricks that have to be used to actually be able to do it. So I would consider this to be, quite a hard problem actually, even though these proofs can be much easier. Okay, so what can we do now? Well, we know that both of these things are equal to X. So we know that 2n plus 1 is equal to 5k plus 4. So yeah, how to get to 10m plus 9? You have to play with this a little bit. And the way I went about this is, and this is where this trick comes into play. Like, this is totally not obvious. This is just trial and error. And so this will be, quite a hard problem for the final exam. Usually the kinds of proofs you see that are element-wise proofs will be much simpler than this. But basically, you want to add 1 to both sides. So you get 2n plus 2 is equal to 5k plus 5. And then we can factor both sides. So we get 2 times n plus 1 is equal to 5 times k plus 1. If I got this right. Okay, great. Yeah. Okay, so because 2 does not divide 5, we know from here that 2 divides k plus 1. So we know that k plus 1 is equal to 2 times some p. So these two steps are the really hard part of this proof, which is why I'm saying, like, this is a pretty hard proof. If we put an element-wise proof in the final exam, it'll almost certainly be easier than this. It'll be much easier to derive it. Okay, from here we know that k is equal to 2 times p minus 1. And now we can plug this back into the fact that x is equal to 5 times k plus 4. So we plug this back into here. And let me kind of switch sides a little bit. I'll continue here. So x is equal to 5 times 2p minus 1 plus 4. And that is equal to 10p minus 1, if I got it right, minus 1. Okay. Okay, so now at this point, we are quite close to here, right? So we have to get to 10m plus 9, and we have 10p minus 1. So, you know, we already have this 10 that multiplies p, which is kind of quite close to 10 multiplied m. This minus 1 is kind of bugging us now. So how do we get to plus 9? We do the following. So we have 10p plus 10 minus 10 minus 1. So we added 10 and subtracted 10. So we didn't move anywhere, but this allows us to group things to get to 10m plus 9. So then this is equal to 10p minus 10 plus 9. And that is equal to 10 times p minus 1 plus 9. And that is equal to 10 times m plus 9. So we substitute m for p minus 1. And so from here, it follows that x is an element of 10m plus 9, where m is an integer. And so this concludes the proof. So like I mentioned, this is a pretty hard element-wise proof because of this trick here that you have to kind of figure out. And that's not easy. But the general structure is here, and you know, you should definitely know the general structure. And so let me now see if there are any questions, and I'm just keeping an eye on time. There's a question in the chat. How do I get it? K plus 1 is equal to 2p. So let me repeat this. So the question is, how did I get that k plus 1 is equal to 2p? So how did I move from this line to this line? So here's the line of reasoning. So we have that 2 times n plus 1 is equal to 5 times k plus 1. So for these two things to be equal, because 2 does not divide 5, for these two things to be equal, 2 has to divide k plus 1. So this is what I wrote here. Remember, this vertical bar means divides. So 2 divides k plus 1. And from the definition of divides, if 2 divides k plus 1, that means that k plus 1 is equal to 2 times some p, where I forgot to write, where p is an integer. P is an element of z. So k plus 1 is equal to 2 times p follows from the definition of divides. So you should definitely know the definition of the divides and how you can express it then and so on. So that was a good question. I hope this makes it clearer now. Any other questions about this proof? Okay, so let me then try to do another one. I have, actually, any other questions about anything? Final exam, what we solved so far? Okay, so let me then try to do one more quickly. Okay, so we want to prove that if A union B is B and B union C is C, then A union C is equal to C. So how do we prove equality? You have to prove two things. You have to prove a subset in this direction and subset in this direction. So let's do the easier one first. So you have to prove both, right? So first we want to prove that C is a subset of A union C. And then we want to prove that A union C is a subset of C. So this is the first thing. This is the second thing. So that's the high level structure of this proof. So now we use element-wise proof for each one of these, right? So for the first one, if X is an element of C, we have to show that X is an element of A union C. And from the definition of union, if X is an element of C, it follows that X is an element of C union anything. And so if X is an element of C union anything, then definitely X is an element of A union C. So this concludes step one. And now in step two, we have this union on the left-hand side. And so now we are going to have two cases. Case one, X is an element of C. And case two, X is an element of A. And in both cases, we have to show that X is an element of C. Well, the first case is trivial. If X is an element of C, well, then it is an element of C. So that concludes case one. That's the easy one. And now case two is the hardest part. So, if X is, so to prove case two, we are actually going to use these assumptions that we have on the left-hand side. So don't forget about these. We have to use them somewhere, and we'll use them in this case too. So if X is an element of A, then we know that X is an element of A union anything. So that follows from the definition of set union. If X is an element of A union anything, then we know that X is an element of A union B. And then from the left-hand side of this proposition, we know that A union B is equal to B. So X element of A union B plus the fact that A union B is equal to B tells us that X is an element of B. Okay? And now we follow a very similar line of reasoning to use this other thing, that B union C is equal to C. So if X is an element of B, then X is an element of B union anything. So from here, it means that X is an element of B union C. And because B union C is equal to C, it follows that X is an element of C. And so this concludes the proof. So I went through this fairly quickly in the interest of time because I have to wrap up now. So this would be, let's say, a medium hard element-wise proof. So there were no tricks that had to be used here, right? You just kind of follow the structure of the proof, you plug in the facts, and you're done. Any questions about this proof or anything else? Okay. This was a unusually low number of questions during these recitations. I hope that means you know all of this. So make sure to practice all these types of questions. Similar questions will be on the final exam. There'll be office hours, so if you're stuck with something, come to office hours. And yeah, with this, I will conclude the recitation. So thank you all for joining. If I don't see you before the final, good luck on the final exam.